Let's see. A particle is subjected to the force given to us in x direction. Which of the following is the correct graph for velocity versus time? So, if particle mass I'm given, net force on it given, so ma I can write down as f naught into e to the power minus of dt. A, which is going to be written as dv by dt, will be equal to f naught by m into e to the power minus of dt. Then what I will do, since they are asking us how v is going to be depending as how what will be the velocity as a function of time, I'll throw dt to the other side. Okay, and it is told the particle starts from rest at origin at t equals to zero. So when t I use zero, our velocity is zero. When t equals to t, velocity will be v. So integrating it left side will have v, right side will be having f naught by m into e to the power minus of bt by minus b. Integration, no problem, no? 0 to t. First I will plug t, will be having f naught by m e to the power minus of bt by minus m. Then minus of e to the power 0 will be 1, will become plus of 1 by b. So what we get is f naught by m. I'll take out common b in case it will become 1 minus e to the power minus of bt. So whenever you come across this kind, see, this is very common kind of. Okay, I'll explain that American that thing again. So when you come across this kind of function, it is very common. In the beginning, you find it difficult, but every chapter somehow it will appear. Okay, it's very common kind of expression. And once calculus gets over in math, so this kind of trouble will be going straight away. So what we have is v equals to f naught by bm 1 minus e to the power minus of bt. Suppose if I'll make t to become very large, then e to the power minus of bt will be tending to 0, that you understand, no? So our velocity will be tending to f naught by b. Remember, no, steady state velocity, similar thing we did, no? Remember, no? So it means this curve must be tending to become equal to f naught by bm if t becomes very large. So the maximum speed it can have is going to be f naught by bm, and that is going to happen at t tending to infinity, that we call it as steady state as well. So which graph is going to give you such kind of curve which increases? And tell me, is it increasing function or decreasing? See, if you don't know how to plot this curve, at least you can tell increasing or decreasing. And if you find the curve is always increasing, how you can find that? By finding out dv by dt. And that we have got, we don't have to find that thing, we know already, dv by dt is f naught by m into some exponential function which is going to be always positive. So dv by dt is more than 0. It means v will be an increasing graph always. So this one gone out of the question picture, this one gone, because it is not always increasing. And the maximum speed can become is this. So it is also gone out of the picture. Since you see the curve is becoming, getting a value more than f naught by mp, that is not possible to recorrect. Understood? No? Virkan, which question you wanted me to explain? Which one? Earlier one? Okay. Understood? No, this one. I was unable to hear you. Can you tell me what doubt you have? Let's check out this question. Question. Yes, sir. What we have is a rope is wrapped around a pole. You grab one end and pull with a tension T1, and the other end is attached to a large object, suppose boat. If the coefficient of static friction, what we have, this rope is wrapped around this pole, which is fixed rigidly on the ground, uh, and the coefficient of friction between the rope and the pole is mu. So, what is the maximum force T2 is going to be for a given value of T1? So you might have seen that thing in real life also near river. bank, they will park their boat by wrapping around a rope around some coconut tree also no, in Kerala and all. So what they have done is, so they will tie that rope 2, 3 rounds around that pole. We are not doing that. We are tying it over an angle phi, and we are pulling it with force T1, and we have to find what can be the maximum possible value of T2 for no slipping happening between the rope and the pole. That should be the question. Correct. And nothing told about the mass of the rope, so you can neglect the mass of the rope or the force of gravity acting on the rope. Let's try this thing. So all of you try it. Tell me, if I'll keep on applying that force T1 and if I'll keep on increasing that force T1 gradually, at the verge of slipping, whatever friction force that is going to be acting on our rope will be this way. Suppose if T1 is becoming more than T2 and it has got tendency to slip this way. If tendency to slip, whose tendency, the rope's tendency to slip is that way, what it is anti-clockwise sense, then friction force, whatever will come, will be coming in clockwise sense. No? In that case, where I have got just slipping about to begin, the friction force will be maximum. So in that case, we can write down, just thinking as if things are happening along that curvature, T1 to be equal to F plus T2. So that is the case when I have T2 to be equal to T1 minus F max sort of thing. So when I can say T2 will be maximum when the slipping tendency will be towards this side. No? Slipping tendency is towards T2 side means the force applied at the point which is attached to some heavier object like boat, that is more than the force that we are applying on the other end. If slipping tendency is in our clockwise sense, then the friction force acting at the limiting case will be maximum, will be in anti-clockwise sense. In that situation, we are going to have T2 to be maximum. So whenever T2 will be maximum, slipping will be happening towards the T2 side. But for friction force to come into picture, there must be some normal contact force. Correct. So how we will determine that? And since friction force is acting on this rope, so in that case, the tension at every point on that rope will not be same, even if I take the rope to be massless. Because when we say tension is same in the case of pulley or string arrangement, when the pulley and the strings are ideal, ideal means massless as well as frictionless and inextensible. So here it is having friction, so tension will not be same at every point. Correct. So what we say is tension will be different at different points. So tension will be little bit also. Correct. Like listening. So tension, whatever will be, is going to be different at different points. So what I will do, if I'll consider some location at an angle theta from the point, maybe this is the point A where the contact at one end begins, and this is the point B where the contact at the other end ends. So from point A, if I'll consider some location theta, so different points will have different theta. So whenever we have circular symmetry, what I told you that instead of talking about some point in space in terms of the coordinate it will have, we can even talk in terms of the distance it is going to be from the origin and at what angle it will be from our positive x, where origin will be the fixed reference point and our positive x is our fixed reference direction. So same here also, I have got these particles of this string. Different points are going to be at same distance from the center, only they are different in their angular position from some place. So what I will do, I'll consider things in terms of the angle. So is it not correct to say that tension is going to be a function of theta? So what I will do, since tension is changing with theta, so I will consider taking a strip which is making a very small angle d theta at the center. and the location of that strip is at an angle theta from the radius drawn through point A. So maybe I'll take a new page, and then what I will do, the element that I have taken, suppose I'll name it as CD, I will draw the free body diagram of CD. I'm talking about the contact that string has over the region CD, whose location, whose angular width is our d theta at the center. Now tell me, whatever the tension force is going to be, will be in action-reaction pair, even it changes at different points. So suppose since tension is going to be a function of theta, so if I change theta, tension will change. So what I have done is, maybe this is my position point A, and I've taken that element at an angular distance theta. So the point C is at an angular distance theta, but the point D is at an angular distance theta plus d theta. So what I will do is, if I'll consider at theta equals to theta, if the tension is T, then if I change theta from theta to theta plus d theta, tension will also change. It will be T plus dt. And the tension is going to be, so in case I told you, if you have a string which is curved, then the tension, first of all, it will act in the same manner as if it will try to increase the length on the section on which we draw the tension force. But at a point, it will be acting in action reaction pair and will be acting along the tangent to the string drawn at that point. So in case the string is curved, then tension is along the tangent. So what I have is, maybe I'll show you the earlier figure. So tension here, it is going to be T like that. And tension here is also going to be an action reaction pair. But what tension I'm indicating? The one that is acting on the section CD, not the one that is acting on the section AC or BD. So the tension at C will be acting along the tangent. So tension at C is T, and the tension at other point, that is D, is T plus dt. So up till here, all of you understood now? And if I will take the component of this tension force in two directions, one is radially inward and one along the tangential direction, the radially inward component of the tension will result into the normal contact force. As if suppose if you are tying a rubber band on your wrist, that rubber band has got some tension, and there will be components of the tension which will be acting inward, which will push the skin of your wrist, because of which, or which way it will be pushing this stress inwards, so you will be having a normal contact force outward. So that everyone can see, like even common sense is only required to tell that there will be a normal contact force and which way it will be and why it will be. Because if I take components of the inwards and in tangential direction, I'll have some net tension force acting in radially inward direction, which will result into the normal contact force. Just what I will do, I will draw the things for that small section PD, but just by drawing it bigger. Okay. So this is our point C, this is our D, and I have drawn a line bisecting our CD in two equal parts. So this angle d theta by 2, this will be also d theta by 2. So tension at C is going to be acting along the tangent and at D as well. So tell me how to get this angle, the angle made by the tension force here with the horizontal. And don't use triangle. You're in 11th class now. So the angle between the vertical and the radius is d theta by 2. So the angle between the one that is perpendicular to the radius, which is OC, is going to be the tangent along which we have drawn the tension force. And the other one, this dotted line which is horizontal, is going to be perpendicular to the vertical. So this two will also have same angle d theta by 2. Whatever way, everyone can tell that angle d theta by 2 it is going to be. So if I'll take the component of the tension forces, so what we have is at D the tension is T plus dt. So if I'll take components, I will have T cos d theta by 2 this side, and here we have T plus dt into cos d theta by 2. And inwards we are going to have forces which is going to be component of T, which is going to be T cos d theta by, sorry, T sin d theta by 2. And other one will be T plus dt into sine d theta by 2. And we know that whenever angle is very small, so what is small here? D theta by 2 is something which is nearly 0. So cos d theta by 2 will be written as nearly equal to 1. Sine d theta by 2 will be written to be equal to nearly equal to d theta by 2. So what is this one will become T plus dt, and dt very small. So what I can say, and this is also going to be T. So I can neglect the dt because dt very small. So what we have is net force in the horizontal direction 0. Net force in the radially inward direction will be T d theta by 2. And this one will be T into d theta by 2. And this one will be dt into d theta by 2. Now if I have two quantities very, very small, suppose x and y, x is nearly equal to 0, y is nearly equal to 0. So x into y is going to be very, very smaller than x. And x into y will be also very, very smaller than y. If I have two small things multiplied, correct? No? If x is small, y is small, then x into y will be very, very small. So x into y can be neglected with respect to x, and x into y can be also neglected with respect to y. This logic, all of you getting it or not? So here what I was doing, with respect to our t, dt was very small, so I neglected dt. But here I have t d theta by 2 plus t d theta by 2 will become t d theta. And this is dt into d theta. So here I have the first term which is itself very small. So if I am neglecting the second term, it should be very, very small. So here t finite, d theta very small. But here dt and d theta both are infinitesimally small. So multiplication of these two can be neglected with respect to t d theta. So it will be t d theta. And what we have is the normal contact force is going to be acting radially outward. That everyone can tell how normal contact force acts. Suppose it is dn here. Okay. Now what we did earlier was we considered slipping happening in clockwise sense. So friction force, whatever will come, will be acting in anti-clockwise sense. Now the CD element, how small it is. D theta is so much small that CD is like a atom thickness small. So something which is an atom thickness small is not curved thing. No, basically it is a straight thing only. So what we have is the friction force that we have got acting is going to be in anti anti-clockwise sense. Suppose it is df, and limiting case it will be mu times the normal contact force. Correct. So we can write down. So what we have is df is going to be, or maybe just a moment. I'll not neglect the dt. Okay, just a moment. So what we have the forces in the horizontal direction. I have got t this side, df this side, and t plus dt this side. It means df must be equal to dt, no? Because I am cancelling out net force in the horizontal direction. So what it is? T plus df must be equal to t plus dt. So I'm not neglecting the dt. Okay, this two will get cancelled. So we have df equals to dt. So df is mu times dn, which is equals to dt. And what is our dn? Dn is t d theta, which is equals to dt. What we can do next is I can separate the variables and then I can integrate this thing. So I'll write down dt by t to be equal to mu times d theta. Then I'll integrate both the sides. When I have theta, see what we have is the point where the contact starts is A, there theta will be 0. Point where the contact ends is B, where theta will be phi. Correct. And the tension that I have got at A will be T1 only because from this end point till A, we don't have any friction force and even it is massless. Correct. So whatever tension I have at this end point, same will be at A. Whatever tension I have at this other end point, same will be at B. So if I'll integrate when theta equals to 0, our T is equals to T1. When theta equals to phi, our T is equals to T2. Integrating it will be getting T2 ln T2 by T1. This integration everyone is able to do, no? Ln T2 by T1 equals to mu phi. So what we have is T2 equals to T1 into e power mu phi. Understood, no, everyone? So what we have got is tension T2 is going to be T1 into e power mu phi, where phi is the angle over which it is making contact with the rope. So suppose if I'll make the rope to be tied twice, wrapped around twice, then phi will become 4 pi. The number of turns you will make that by that much amount, our tension will become exponentially increased sort of thing. No? Understood? So more number of turns will give us more force at the other end that we understand also practically. So I hope all of you understood this thing.